going to be talking about inverse trig functions, but before we get started with the calculus part of that, we're going to go ahead and review some of the trig. So most of this is familiar to you because of your trig background, but let's go ahead and have a look at what inverse trig functions are, how they're defined. Let's just look at one case. We have 6 trig functions, but I'm just going to focus in on the sine to start with. So if we look at the sine graph, this should be familiar as well, and all these values come from the unit circle. So the sine of 0, we'll just make a quick little table here, is 0. The sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is negative 1. The sine of 2 pi is 0. And then this would be, if we kept going around the unit circle, we'll just go one more point past this. We'd be at 5 pi over 2. Sine of 5 pi over 2 is up here at 1. So you can see that this pattern that it follows, and then I'm going to run back this way as well to negative pi over 2. That's negative 1. Okay, so this is what the sine curve looks like. And this would be something I would expect that you would know because it's really helpful when we're going to be working the calculus part of these. So this is the sine curve. Now I want to know, we're talking about inverses up here. Does the sine curve have an inverse? And right away it fails the horizontal line test, so there's no inverse that exists. So HLT, horizontal line test, so no inverse. Well, that's going to make this a short section, right? If there's no inverses. So what we have to do though is we have to say, well, I really want it to have an inverse though. So what do I do? Well, we want it to have an inverse, so we restrict the domain so an inverse exists. Now there's a lot of different ways that we could restrict it. We could restrict it from 2 pi to 5 pi over 2, passes the horizontal line test. From 3 pi over 2 to 5 pi over 2, it passes the horizontal line test. From pi over 2 to 3 pi over 2, it passes the horizontal line test. So we can see there's a lot of different regions that I could do this on. Well, these are the kind of the criteria I want to keep in mind. I want to have as much as possible, so I don't want to choose just one quadrant. I want to be able to choose as many quadrants as possible. So for instance, from 3 pi over 2 to 5 pi over 2 is 2 quadrants. And I want it to be some common angles near the origin. Okay, so if we came over here, let's say 0 to pi, it doesn't pass the horizontal line test. But from here to here, it does pass the horizontal line test. So that's where my domain restriction is going to be. And this is kind of universally accepted to be the domain restrictions for sine in order for their inverse to exist, because there's an infinite number of ones that I could choose from, but I'm choosing one that's close to the origin. So the way I'm going to restrict the domain is I'm going to restrict it to negative pi over 2 to positive pi over 2, points inclusive. That's why I have a bracket there. So this will be the region for my restricted domain for sine, and then I can see right away, an inverse does exist. It does pass the horizontal line test there. Now the points are included at the end because I can actually plug in pi over 2 and get a value of 1 back out. So that's my restricted domain. Now we could do this same exact step process, graph the function, find the best restriction, but we've done it for sine, and I'm just going to write out what they look like for the rest of the trig functions. Now those restrictions I would expect that you would know for sine, cosine, and tangent, and the rest of them we can just look up. So let's look at y equals sine of x, and let's also look at arcsine. Now I guess we should talk about notation real quick. So notation here for inverse sine, there's a couple different ways that you might see it. You might see it as arcsine of x or inverse sine of x. And this inverse sine with this exponent up here that's a negative 1, sometimes that causes a little bit of confusion. Please remember that this does not equal 1 over sine of x. It doesn't mean to reciprocate. This is an entire function, so we're not reciprocating here. We're just saying the inverse of the function. So this book uses both interchangeably, but predominantly as I've been looking through, they use arcsine. And I have to tell you that I have used this notation, inverse sine, for 30 years, so it has been a challenge for me to write everything out using arcsine, but I'll try to be very careful about using both notations, but predominantly arcsine to match what you're going to be seeing. So when we make this table, I also want to be able to talk about the domain and the range. So I'm going to call that domain and range. So the domain we just talked about to restrict pi was negative pi over 2 to pi over 2 points inclusive. And then the range for that gave me a graph that only went from negative 1 to 1. So here's the domain, negative pi over 2 to pi over 2 points inclusive, and the range went from negative 1 to 1. It covered this whole green region. Now remember, what happens between a function and an inverse is the domain and the range swap. Okay, so this is going to come down here. Negative pi over 2, whoops, to pi over 2 would be the range. That means my answer has to lie here, and my domain would be negative 1 to 1. Okay, so let's think about what this means. The output for the arc sine or inverse sine is negative pi over 2 to pi over 2. That's an angle. That's good to remember. Now another thing I want you to think about is if we look at negative pi over 2 to positive pi over 2 and we're talking about arc sine, I'm only looking at the right half of the unit circle. So everything I answer has to lie within this for my solutions. Sometimes for me, it's easier to remember this picture for my restrictions than this. Okay, so if the picture helps you, remember that. Now, a couple quick things. I can't go outside of this picture, meaning I couldn't come over here and travel back here to find my answer. What I would have to do is just move here to find my answer, rotating clockwise instead of counterclockwise. So let's look at a quick example. What angle, whoops, let me write out the problem first and then I'll write out the answer. Let's do arc sine negative 1/2. Okay, this means, and then you should write this out every time you see arc sine, arc cosine, arc tangent, arc any of the trig functions. You should write these two words, what angle? Because the most common mistake that people make for these is they don't understand they're looking for an angle. They're just looking for some number. So this means what angle in the interval, negative to positive pi over 2, has a sine of negative 1/2. Well, you know your unit circle, so you'll probably know the answer to this. Maybe it'll show up. Let's try that again. If you don't know your unit circle, you might want to put that on your list of things to do. Oh, I guess it did show up really tiny over here. Because you'll need to fill this out at the beginning of each exam. It is so important that you know your unit circle. It'll just make your life so much easier, because if you have to look up something every single time, that's all you're going to get done is looking up trig stuff. So remember, for arc sine, I'm only in this region right here. I can't move outside of it. I can't rotate on the other side. I'm just in this region. So basically, I'm looking for an angle in this region that has a sine of negative 1/2. Okay, well, sine is negative down here in quadrant 4, and here is where I have negative 1/2 for my sine, and that looks to be 11 pi over 6, but that is not my answer. 11 pi over 6 would start here and rotate clear through, and I can't move outside of here. Okay, so I have to end up here, but I can't go outside of here, so I need to think about negative angles. So this would be negative pi over 6. That would be the same angle, coterminal part, just a different amount of rotation. So my answer here is negative pi over 6. So these angles right here, I need to make sure that you readjust them to represent negative angles. Okay, so that's for inverse sine. Let's look at inverse cosine and inverse tangent next. And again, those are the three that I would make sure that you have on the tip of your tongue. So y equal cosine of x and y equal arc cosine. And this could also be inverse. So this is domain and range. So how am I going to restrict cosine? Well, I'm going to restrict it from 0 to pi. My range would be -1 to 1. And then remember that these swap. So the range here and the domain here, because remember they do swap. Okay, now if you want to go back and graph the cosine and see where that comes from, that would be great. I want to focus more on the inverse part, so let's go ahead and do the same thing we did up here. Let's write out a problem and use that unit circle. So let's look at arc cosine of -square root of 3 over 2. So again, whenever you see arc anything, you need to think of two words. What angle? What angle in the interval 0 to pi, and that comes from right here, has a cosine of -square root of 3 over 2. So we're working exclusively in radians. Let's put that unit circle up again. Okay, now we're going 0 to pi here. So 0 to pi would be up in this part of the unit circle. Now I can't move outside of this. I have to stay within here. Okay, so now cosine is negative in quadrant 2, and I'm looking for cosine of -square root of 3 over 2. Now square root of 3 over -square root of 3 over 2, cosine is my first value, because all the values here are listed as cosine sine. So cosine comes first, sine comes second as my ordered pair, and this refers back to 5 pi over 6. Now 5 pi over 6, I have not left this green region, so I'm fine to leave it as 5 pi over 6, and that's my answer. Let's do the same thing for tangent. Now when we're working with tangent, I need to remember that I have vertical asymptotes when I'm working with tangent, because remember, let's recall tangent is equal to sine over cosine. So I have vertical asymptotes wherever cosine of x equals 0. So my domain here is the same as sine, except this goes from negative to positive pi over 2, but the points are not inclusive, and the reason I don't have brackets here is that cosine of x equals 0 at negative and positive pi over 2, so my fraction would be undefined. Okay, and then we remember the domain and the range swap here. So the range is negative to positive infinity for my original function, and negative to positive pi over 2 for my arctan or my inverse function. Okay, now I guess when I look at these, I don't really focus on memorizing them so much as understanding them, but you do need to know these restrictions. So for tangent, it's the same as it is for sine, except I can't include those endpoints. And so the way I kind of remember that is I put a big hollow point here to remind myself of that. So let's go ahead and write out one of these. Let's look at arctan, and let's do square root of 3. So this means what angle in the interval from negative to positive pi over 2, points not inclusive, has a tangent of square root of 3. Okay, so let's go ahead and put up that unit circle. Now this unit circle doesn't give me tangent. There are no tangents on here. Okay, but I can remember a couple of things. Remember, we're going from negative to positive pi over 2, points inclusive, or sorry, points exclusive for tangent. So that means I can't actually reach these points at the end. So I'm going to put big hollow points there to give me that reminder. So I can't move outside of this region. So tangent is positive in quadrant 1, so I know it's going to be a quadrant 1 angle. So let's have a look. If we can't remember the tangents, which to be honest with you, I can't. I always have to start from scratch to find tangent. I always look at the ratio of sine over cosine to help me out. So let's look at pi over 6. So this would be sine of pi over 6 over cosine of pi over 6. Sine of pi over 6 is 1/2. That comes from right here. Cosine of pi over 6 is square root of 3 over 2. When you divide by a fraction, you multiply by the reciprocal, so I get 1 over root 3, but when I rationalize that, I get square root of 3 over 3, so it's not pi over 6. And this is the same thing I do every time. Then I think, oh yeah, I remember that now. So let's try pi over 3. So the sine of pi over 3, I can come right up here and grab that, is square root of 3 over 2. And the cosine of pi over 3 is right here as well, as 1/2. Well, when you divide by a fraction, you multiply by the reciprocal, and there's my root 3. There's my root 3. So my answer here is pi over 3 is my answer. Now after I do this, and it's every single time for some reason I do this, I think, oh, look at this. If I can remember that 3 plus 3 is 6, that should give me that reminder. And here I just get root 3 for tangent of pi over 3, and it's just 3. So that is how I remember it eventually after I get going on these, but the first few times I always have to stop and have a look. Okay, so now we have all of our other trig functions, and I don't expect you to remember these. These are something that we could look up, but I'm going to go ahead and write these out, and you can hit pause if you'd like to and copy them down. They'd be handy to have in your notes. So here's for cotangent and arccotangent. Here is secant and arcsecant or inverse secant. Okay, and here are the domain restrictions, domain and range for cosecant and inverse cosecant. So again, I don't think you should memorize the ones for cotangent, secant, and cosecant inverses, but you should remember the ones for secant, or sorry, for inverse sine, inverse cosine, and inverse tangent. And remember, there's kind of some shortcuts to that. Tangent and sine share the same thing. I just don't have the endpoints for tan. And then I can also remember that for cosine, I'm in first and second quadrants. So for these, I don't remember necessarily all of this stuff. I remember the picture. So for me, when I think about arc cosine or inverse cosine, I think, oh, quadrants 1 and 2, this picture right here. Next is looking at some problems. Well, we've already looked at a couple, but let's look at a few more. So whenever you see inverse sine, inverse cosine, inverse tangent, you should be writing out that question, what angle, what angle, what angle. Now we're going to be using our unit circles a lot. There's some blank copies you can print out on the My Math Lab page, and I would encourage you to print that out and practice filling it out from memory, because you'll need to do that at the beginning of every exam, is to complete that from memory. Okay, now as you're memorizing it, if you don't already have it memorized, keep one handy, because you're going to be using this all the time and you want to get used to looking at that paper reference. So if we have a problem like this means what angle in the interval from negative to positive pi over 2, that's quadrants 4 and 1, has a sine of negative square root of 3 over 2. And that's the question you should write for every one of these. It really helps in understanding what's being asked of you, and it helps in answering it as well. Okay, so here's that unit circle. Now remember, for arc sine, I'm in quadrants 4 and 1. I can't move outside of there, and all of my angles have to lie within here. So negative sine is going to be in quadrant 4, so this tells me it's quadrant 4. So I'm going to come over here and I see negative square root of 3 over 2. Well, that's 5 pi over 3, but that's not my answer, because to get to 5 pi over 3 I would have to go outside of that shaded region. I have to go clockwise and find that angle, and that coterminal angle to 5 pi over 3 is negative pi over 3. So that is my answer here, negative pi over 3. Okay, and again, we're working in radians. So every time you see a question, you should be writing out the words, if it has an inverse trig function, what angle. Let's look at arc cosine. Let's do negative square root of 2 over 2. So this means what angle in the interval from 0 to pi, because cosine is 0 to pi, has a cosine of negative square root of 2 over 2. And if you write this out every time, you will be much more likely to get these correct, just because you'll understand what you're looking for. A lot of people, when they work with these, they're answering the wrong question. So if you can write the question correctly, it's more likely you'll get the answer correct. Okay, so here we are. So cosine is negative. Okay, so that would be quadrant 2. So let's come over here to quadrant 2. Cosine is negative square root of 2 over 2 right here. Now to get there, I never had to leave this region, so 3 pi over 4 is a fine answer here. I don't need to look at the negative of it. Okay, so that's using your unit circle to help you come up with those. Now we can also combine these, and these are really fun. Let's look at the tangent of the arc sine of 1 over the square root of 2. Okay, now usually we would see this in rationalized form as square root of 2 over 2, and then right away it's familiar to us. So this is asking us the question right here: what angle in the interval from negative to positive pi over 2 has a sine of square root of 2 over 2? Okay, and the answer is going to be pi over 4. Okay, we can see that coming right up here. Here we're restricted for inverse sine right here, but I can see square root of 2 over 2, pi over 4. So what I do is I plug that in then back to my tangent. So that would be tangent pi over 4. And tangent of pi over 4, if you don't remember, the value for that is sine over cosine. So any tangent or cotangent of a multiple of pi over 4, whether it be pi over 4, 3 pi over 4, 7 pi over 4, is either 1 or positive 1, depending on where it lies, because the sine and cosine are the same. So in quadrant 1, the sine is square root of 2 over 2. Anything divided by itself is 1. So this entire expression simplifies to 1. Okay. Now you can also use your calculators to figure out, let's say if you had arc sine of 1, something like that, you can definitely plug that into your calculator, but the standard angle ones you should know. Now sometimes there is no such angle, meaning I'm trying to find an angle that doesn't exist because the sine is outside of the particular domain. So be prepared for those as well, and make sure you're in the correct degree or radian mode depending on the question that's being asked. Okay, derivatives of inverse trig functions. This is important. You might want to put these on a note card. I will have these on a formula sheet for you. But I would have them very handy so you can access them pretty easily. So derivative is inverse trig functions. And again, I will give these to you on a formula sheet. So on the test, on a formula sheet. So here the derivative of the arc sine of u is equal to 1 over the square root of 1 minus u squared du dx. So that just means after I identify my u, I square it and it goes in here, and then I need to remember to take my derivative of u. Sometimes you'll see this notated u prime. Okay, let's look at derivative with respect to x of arc cosine of u. Well, it's identically what we just did above, except it's negative. Let's look at tangent, arc tangent. And u is usually some function of x. This is going to look like 1 over 1 plus u squared du dx. Okay. Now the reciprocal of sine is cosecant, so let's do cosecant next. Arc cosecant of u is equal to, I'll tack on that du dx on the end, negative 1 over the absolute value of u square root u squared minus 1. The derivative with respect to x of the arcsecant of u is the same exact thing, except it's just a positive one. Okay, next we're going to look at arc cotangent, and it's going to be exactly the same as tangent except negative. Okay, so we'll want to keep these somewhere nearby because we're going to refer to them often, because we need to know that form of these when I work with derivatives. So what we're going to do is work quite a few derivative problems and see how the forms work. So the first one, I would like to find the derivative with respect to x of arc sine of x squared. So this means what angle between negative and positive pi over 2 has a sine of x squared? And the answer is I don't know, because I don't know what x is. Okay, but we can still figure this out. Now for here, we are going to use the derivative with respect to x of arc sine of x equals 1 over the square root of 1 minus u squared du dx. So that's our form here that we're going to use. So what I need to do is identify u. So u here is equal to x squared, du is equal to 2x dx. So when I write out my derivative, all I do is fill in the form. So I have a 1 square root of 1 minus u, which in this case is x squared quantity squared, times 2x, which is my du dx. And then I simplify this up a bit, and that's my derivative. So 2x will go on top, square root of 1 minus, now x squared squared is x to the 4th. So there's my derivative. So I find my form, use the form, find the pieces and parts, and fill it in. Now I can combine these with product rules, chain rules, quotient rules, and then that's when they really get interesting. So along those lines, let's go ahead and look at the derivative with respect to x of the arc tan of 3x quantity squared. Now let's be careful how this is written. I'm not squaring the 3x, I'm squaring the arctan of 3x. So that's why these brackets are here, because that changes the problem. Okay, so this is going to be a chain rule. So to run this chain rule, what I would do is I would bring the 2 down and then decrease the exponent by 1, leaving that bracket in there, and then I multiply it by the derivative within, which is the arctan of 3x. So this is the outside part of the chain, and this is the inside part of the chain. So the derivative of the outside times the derivative of the inside. So let's go ahead and focus on this derivative. So for this derivative, u is equal to 3x, du is equal to 3. Now the form that we are going to use here is the derivative with respect to x of arctan of u is equal to 1 over 1 plus u squared, and then that du dx. So this derivative would be 1 over 1 plus u squared, but u was 3x, and that has to be quantity squared, okay, times du dx, which would be 3. So this would be 6 arctan of 3x all over 1 plus 9x squared. That's the derivative. Okay, so the 6 is out front. 2 times 3 is 6, arctan 3x, and then I usually would make sure when you write this that this 3 and the x are in parentheses. Okay, next let's go ahead and look at another derivative. Let's look at the derivative with respect to x of arc cosine of negative 3x squared plus 7x. Okay, so I'm taking a derivative here, so I'm going to write my form over here just so I can look at it while I'm putting the pieces and parts together. This is the arc cosine of u is equal to negative 1 over the square root of 1 minus u squared du dx. Okay, so here u is negative 3x squared plus 7x, du is negative 6x plus 7. So those are the things that I need to keep in mind. So this is going to be a negative 1 square root 1 minus u, that's that binomial quantity squared, and then I'm going to multiply that by du dx, which is negative 6x plus 7. So let's go ahead and rewrite that. So what I'm going to remember here is this negative is times all of this, not just the negative 6x. So I have to distribute that, and I have 6x minus 7 over the square root of 1 minus negative 3x squared plus 7x quantity squared. That's my derivative. Okay, now if you wanted to, you could FOIL this out and combine like terms, but I think that looks pretty good the way it is. So those are some examples of some pretty basic derivatives. We did a little bit more complicated one, but something I want you to keep in mind is that these can be combined with anything that we're used to working with in terms of product rule, quotient rule, chain rule, any of those. We can combine them with logs, e to the x, all those transcendental functions. So don't be surprised if you see some combining of those, but again, the technique is still the same. The same basic rule, let's say like the product rule, I just have a new function that I can take the derivative of. I can also look at the integrals here of these forms, and they're actually the antiderivative of the ones we just looked at. So if I have something that's of this form, this matches the inverse sine or the arc sine. So the integral here, if it matches this form, would be equal to arc sine of u over a plus c. Okay. If I had something of the form 1 over a squared plus u squared du, that's going to be 1 over a arctan of u over a plus c. Now we don't do one for arc cosine because the only difference would be if I had a negative here. And we don't do one for arc cotan because the only difference would be if I had a negative one here. So the next one that we'll look at is the integral for arc secant. So it is of the form absolute value of u in the denominator, u squared minus a squared du. This is going to equal 1 over a arc secant, oh sorry, got to get used to that notation, arc secant, absolute value of u over a plus c. Now these will be on a formula sheet. I don't expect you to memorize these, but I'd keep them on a note card if I were you, very handy, or print out the formula sheet, because you're going to refer to these often. And if you can start recognizing this form, and you know it goes right to arctan, that's going to be a lot easier for you than if you're trying all these different u substitutions until you can kind of come up with that. So these will be provided to you. You do not need to memorize them. Okay, so let's go ahead and look through quite a few of these, as many as we have time for. Let's look at the integral of x over the square root of 1 minus x to the fourth dx. And of course, that's how my math lab writes it. I always like to pull my dx's out so I can focus in on the integrand right here. Okay? So one thing I might try here is I might say, oh, okay, let's let u equal x to the fourth. du would be 4x cubed. I don't have that. I have an x, but I don't have an x cubed for sure, and I can't really do anything about the missing x squared. I could compensate with the 4, but this doesn't match. Okay, let's try something else. Let's let u equal 1 minus x to the fourth. du would be minus 4x cubed. Still don't have that. So this is at the point where I think, I wonder if this fits one of those forms. If I could make this look like a squared minus u squared, then this could work. So this fits the form a squared minus u squared, so I think that this will fit the integral square root a squared minus u squared du of inverse sine of u over a plus c. Okay? So that fits that form if I can make it work. So let's look for our pieces and parts. So u is just equal to x squared because it's the base here, so I'm not using x to the fourth. Du would then be 2x dx. So if I multiply by 2 on the inside, compensate with the 1/2 on the outside, I have that 1/2 on the outside that I compensated for. Now this 2x dx becomes my du, and then in my denominator I have a squared minus u squared. Well, what was a? A is just 1 in this case. So writing this out, I have a 1/2. Okay, so this all fits what I need now. So this is arc sine of u over a. But I know what u is, x squared over 1. Which is just x squared plus c, my constant of integration. So again, if you don't recognize it, you're going to make all these trial and errors until you do figure out how to make it fit a form. Now sometimes it doesn't obviously fit any form, and I have to do some algebra on it to get it into a spot where it actually will work. So let's look at 4x squared plus 4x plus 2 over 1 dx. Now the first thing I see here is there's no square root sign, so if it does fit a form, it's not going to be inverse sine or inverse secant, it'll be inverse tangent if it fits a form, because they both have square roots, inverse tangent doesn't. But let's go ahead and try a few things on this. If we let u equal 4x squared plus 4x plus 2, du is 8x plus 4. No, I don't have anything close to 8x plus 4 up here. Okay, let's keep trying. Let's try something different. Maybe I could rewrite this. Maybe I could pull a 2 out, and I'd be left with 2x squared plus 2x plus 1. And then maybe this factors further, but this doesn't. This doesn't factor any further, so I'm done. I thought maybe if it factored further, it might be something like a binomial squared, but it doesn't. So this doesn't work either. So let's look at this 4x squared plus 4x plus 2 again. And let's do something called completing the square, again from algebra. Because if I can complete the square, I can get this looking like something like a squared plus u squared. So now let's review completing the square real quick. What we do is we factor out the 4, so my leading coefficient is always going to be positive. Positive 1. So I factored out the 4, this is now a positive 1. So when I factor out the 4 here and here, this is what I'm left with. Now the 2 I'm not going to put in the parentheses, it's going to go on the outside because I have to use that for my constant component. Now when we complete the square, what we do is we take half of the linear term. So this is an implied 1 right here, so half of that is 1/2, and I square it. And I will add this to both pieces. Now I just don't add the 1/2 squared here because remember there's the 4 out front, so that's 4 times 1/2 squared. Okay, so that's completing the square, and again that's a technique that you learned in college algebra. So this factors now, and I could show one more step here. This factors now into 4 times the quantity x plus 1/2. Actually, I'm going to back up one more step. X squared plus x plus 1/4 plus 2 plus 4 times 1/4 is 1. So 1/2 squared is 1/4. 1/4 times 4 is 1. So the way that this will look is x plus 1/2 times x plus 1/2 when I factor it plus 3. 4 times the quantity x plus 1/2 squared plus root 3 quantity squared. Okay, let's keep going with this. This is kind of interesting. So remember, I'm trying to make this fit the form a squared plus u squared du. And I think I'm almost there. I can't pull this 4 out front because it's attached to only one term. So what I can do, however, is rewrite it as 2 times the quantity x plus 1/2 And then all of this is squared plus square root of 3 over 2 squared. Then I can distribute 2x plus 2 times a half is 1 squared plus root 3 squared, and there we are. There's my u squared plus a squared. That's what I was looking for. So again, I'm trying to make it fit this form. And u squared plus a squared plus u squared, doesn't matter. Order doesn't matter when we're adding. It's the additive identity. I think actually it's called the commutative property of addition. Okay, so let's write this out. So I have root 3 quantity squared plus 2x plus 1 quantity squared dx. Now I can start identifying my u and my du, and I have my a as well. So everything fits. So the only thing I don't have is that 2 dx right here. So I'm going to multiply by a 2 on the inside, compensate with a 1/2 on the outside. And then I have 2 dx is du. And then I have a squared plus u squared. Okay, so I'm dragging along this 1/2, but the form for this is 1 over a arctan u over a. So 1 over a is root 3, arctan u over a, u was 2x plus 1, and a was root 3 plus c. And of course we can clean that up a little bit. So completing the square was a huge thing here. So back in the day when you were taking algebra class and you worked on completing the square, this prepared you for this day right here. Completing the square does actually show up fairly often. So let's go ahead and clean this up a bit. So this is 1 over 2 root 3 arctan 2x plus 1 all over root 3 plus c. That is your integral. Okay. Now if you had to evaluate this, then you'd say, oh, I'm going to integrate this from, square root of 3 over 2 to 4 or something like that, and then you would do that next. So when you look at the big picture, this looks extremely complicated. But if you can break it up to its smaller parts and do one small step at a time, it's not too bad. And then also think about being very, very diligent and precise about showing your work, because that really helps you step through these than skipping steps, because there is a lot going on here, especially with the completing the square on this. Okay, let's just continue on to work quite a few of these. I think the more problems that we work, the better we'll get at these. We'll start to see some patterns and it will become a lot more simple. Okay, so as usual, when my math lab gives us a problem, they always put that dx there. It drives me nuts. Okay, I like to just look at the integrand. I don't want to worry about the dx, because this is really the only piece I need to focus on to get started. This is just extra information right now. It needs to be there, but it's just extra. Okay, so usually we'd start this and we'd say, okay, let's let u equal 3 minus 4x squared. Du is a negative 8x dx. Okay, doesn't work because I don't have a negative 8x. So I'm going to have to rework this and think, okay, could this fit a form? And I think the answer is yes, it could fit a form. So let's see, this looks like it has a square root and it has a minus here. So this could look like a squared minus u squared du is equal to inverse sine of u over a plus c. So let's try that one. That might be a good fit for this. Obviously we have a little bit of work to do to get it to that point though. So this is equal to square root of 3 quantity squared minus 2x quantity squared 1 dx. Okay, so it looks like a is equal to root 3, u is equal to 2x, du is equal to 2 dx. So I'm missing the 2 on the inside, compensate with the 1/2 on the outside, and let's see what I have then. I have 1/2 integral 2 dx is du, And then my a squared minus u squared is all there. So this does fit the form. So the 1/2 is from compensating for this 2 being gone. So that's where that comes from. It doesn't come from the formula up here. And then this is inverse sine, dang it, arc sine. The notations are the same. So arc sine inverse sine of u over a. So I have 1/2 arc sine of u, which is 2x over the square root of 3. And then this is plus c, my constant of integration. Now you might rationalize that, so this could be another form. So that would look like 2 root 3 over 3 times x plus c. So either one of these would be correct. So again, find the form that it fits. And usually what I do is I look at, is there a square root? If there's not a square root, I know right away that it's probably an arctan if it's anything. And then if it's a squared minus u squared, it'll be arc sine. If it's u squared minus a squared, it'll be arc secant. Okay, now everything we've done so far has just been nice little dx's. Let's look at one that might have a transcendental component to it. So right away here I see a square root, and I see a squared minus u squared. So actually this is u squared minus a squared. This is arc secant. Now one thing I'm missing though is this thing out front for arc secant. So let me write that out. So arc secant looks like 1 over u square root of u squared minus a squared du, and that's 1 over a inverse secant absolute value of u over a plus c. And that 1 needs to be centered. Okay, so I'm going to try and get it in this form. And when I look at this, I'm thinking, I don't have this piece right here at all. But maybe with some substitution, I can get it to that point. I'm going to pull this dx over here. And then when I rewrite this, this is going to look like e to the x quantity squared minus root 6 quantity squared. Okay, so I'm getting somewhere here. So let's let u equal e to the x. Du is equal to e to the x dx. And then a for this particular case is root 6. Okay, so dx e to the x. Wow, look at this. If I multiply by an e to the x here, I can divide by e to the x down here. I can't pull it out front because it's not a constant, but essentially I've just multiplied by 1 by multiplying top and bottom by e to the x. So when I rewrite this, e to the x dx becomes my du, and then u is e to the x, and e to the x is always positive, so this is my u. And then this would be u squared minus a squared. And it fits perfectly. So this is going to integrate into 1 over a arc secant absolute value u over a. So we just fill in what we have here. 1 over a arc secant absolute value of u over a plus c. And if you want to, you could rationalize those radicals. Okay, but this fit that form perfect. And this does not happen very often where I get a chance to do this to make that work. Okay, so that was an interesting part of this question. So these are not short problems, but if you break them down small steps at a time, show all of your substitutions, and again, be really diligent about showing your work with that, these aren't too bad. So let's integrate from negative to positive pi over 2. 2 cosine of theta over 1 plus sine of theta quantity squared d theta. Now this doesn't really look like anything. I mean, it doesn't look like it fits any forms. So you might look at this and say, well, what if I just let u equal sine? Well, du would be cosine, and that would be good. But I don't have anything to do with this 1, so I have to make sure I have all my bases covered. Now, because there's no square root sign here, and it's an a squared plus u squared in the denominator, it might fit the inverse tangent form, which would integrate into 1 over a inverse tangent u over a plus c. Okay? So So let's see what we can do about that. I think we can pull that 2 out front to start with. I'm going to rewrite the 1 as just 1 squared just so it fits that form nicely. So u would equal sine of theta. Du is equal to the cosine of theta d theta. And let's see what we have here. So cosine theta d theta is my du. So there's my du. In the denominator I have a squared. We didn't write that down here, but a is 1. So a squared plus u squared. So I have the 2 out front because of my 2 that I need here. Why did I need the 2 there? Let's check back. Oh, 2 from the original right up here. And then that integrates into 1 over a, 1 over 1, arctan u over a. And a is 1 in this case. So this has integrated into 2 arctan of the sine of theta. Now this is evaluated from negative to positive pi over 2. So this is 2 arctan. I'm going to run out of room. Let's see. This is equal to 2 arctan sine of pi over 2 minus 2 arctan sine of negative pi over 2. Okay, so let's write this out. We know the sine of pi over 2 because we know our unit circle. The sine of pi over 2 is 1. We know from our unit circle the sine of negative pi over 2 is negative 1. Okay, so let's think about this. Now, every time we see an arc sine, arc cosine, arctan, any of those, that means what angle, what angle, what angle. So this means what angle in the interval from negative to positive pi over 2, endpoints not inclusive, has a tan of 1. So what angle in the interval from negative to positive pi over 2 has a tan of negative 1? So for this one that would be pi over 4. For this one that would be negative pi over 4. Okay, so that would be 2 times pi over 4 minus 2 times a negative pi over 4. So this would be 2 pi over 4 plus 2 pi over 4 is 4 pi over 4, which reduces to pi. So all of that describes pi. So knowledge of your unit circle, if you have it at your fingertips, if you have it memorized, will make your life so much easier when we're working through one of these problems. So instead of focusing on problems that are like the small stuff, like the trig and the algebra, you can focus on the calculus. Okay, I'd like to do 3 more questions. I don't know if we'll get time, but I know the more I go through here, the more it'll help you out. So let's see how many we can get done. So let's look at x plus 4 over x squared plus 4. So here we might start with u equal x squared plus 4. Du is equal to 2x dx. I kind of have it, but then I have this extra plus 4, so that doesn't work. But I also notice this looks like a u squared plus a squared. It's like I have parts and pieces of a lot of things going on here. Let's split it up. I think that'll work. So let's put x over x squared plus 4 dx. So this is called separating the numerator. And so now I have 2 different integrals and I have 2 different techniques to use. So here I'll use that u substitution I was just looking at. So I'll multiply by 2 on the inside, compensate with the 1/2 on the outside for this one. And this will look like 1/2 integral 1 over u du, which integrates into natural log absolute value of u. and u was x squared plus 4. So there's that piece. Now this one is perfectly set up for inverse trig. I'm going to use a different variable for my substitution. W is equal to x, dw is equal to dx, and then a is equal to 2 here because a squared was 4. So this 4 I can pull out. So this looks like, okay, I have it all, 1 over a squared plus u squared du. So that integrates into 1 over a arctan u over a. Okay, so let's fill in what we know. 1 over a arctan u, or actually this is w. I should be using w. Let me put these w's back in here. Okay, and then w was x over a. So simplifying from here, I have 1/2 natural log absolute value of x squared plus 4, plus it helps to cancel these and give me a 2 arctan x over 2 plus c. Okay, it's a lot going on there. This one we split it up, and you can separate the numerator. You can never separate the denominator though, unless it's in factored form. Just an algebra topic. Let's look at integral from 0 to 1 of arctan of x all over 1 plus x squared dx. So for this one, I'm going to I can't integrate arctan, so it has to be my u. So let's let u equal arctan of x. Du is 1 over 1 plus x squared, because that's the derivative of arctangent of x. And in this case, I have all that. So when I rewrite this, I'm going to drop my limits of integration. So I have u, and then all of this is my du. So I don't even need a fraction. This is just u. This is just u to u. Okay, that's exciting. So that integrates into u squared over 2. So here I have arctan of x quantity squared. You need to make sure you have your brackets there over 2. And now I'll evaluate it from 0 to 1. So let's plug in that 1 first. That'll be arctan of 1 quantity squared over 2 minus arctan of 0 quantity squared over 2. Now remember, what does arctan of 1 mean? So we'll do that off to the side. So arctan of 1 means what angle in the interval negative to positive pi over 2 has a tangent of 1? And the answer to that is pi over 4. Let's look at our second one, arctan of 0. This means what angle in the intervals negative to positive pi over 2, points not inclusive, has a tangent of 0? And the answer is 0. So that's what's going to go in here. So this would be pi over 4 quantity squared over 2 minus 0 squared over 2. So this is pi squared over 16 all over 2, and I could rewrite that as 2 over 1. And I'll multiply that by 1/2, so I get pi squared over 32 here. Okay, so these are getting more and more complicated, kind of relying on your algebra, trig, and calc 1 skills as if they're firmly in place, so we can focus on the complexity of the new forms in the problem. I just want to do one more. I know this is getting long, but I want to do one more. If you don't think this example will be helpful to you, once you see me set it up, you're welcome to fast forward through it or quit. It's up to you. So this looks like the integral x 5x squared minus 4 in the denominator, dx in the numerator. And again, I am going to pull that dx out here. And I think this is going to fit a form, so I'm going to rewrite this as root 5 quantity squared minus 2 squared. Okay, now this looks like an inverse secant. Okay, so let's write that down. Let's write that form down. So the integral of u squared minus a squared du is 1 over a inverse secant absolute value of u over a plus c. Okay? So let's go ahead and write everything out here. U is equal to root 5, and notice that x is not under the radical. Du is just root 5 dx then, and then a in this case is 2. So I have everything I need there, I think. Let's check it out. So I have the root 5 quantity squared. Looks like to me I just need the root 5 right here. And then for my du I need the root 5 up here. So really I'm just multiplying by 1. So rewriting this then, this looks like the integral of u square root u squared minus a squared. Okay, so this integrates into 1 over a arc secant absolute value u over a plus c. Okay, so that's an example of using compensation for the u, and it turns out that it worked well for the du as well. Okay, so we covered a lot here. Hopefully I covered some good integrals, good derivatives, some good inverse trig information that'll help you out on this assignment. Remember, you have all of your earlier integration techniques. Don't think that we're just stuck with these that we've learned in this particular section. We have product rule, quotient rule, chain rule. We have, especially the chain rule, we have new functions that we can take derivatives and integrate now. So put them all in your toolbox and make sure that you're aware of all of them and can use them as needed. As usual, if you have any questions, let me know. I'm always happy to help. Good luck.